Hello, my awesome chemists. Today we're going to talk about polarity and polar covalent bonds. So let's start by talking about what covalent bonds are. So covalent, we already talked about this, meaning that electrons are being shared. Co means together, valent means valence electrons. So in covalent bonding, the electron clouds are being shared. Those valence electrons are being shared between two atoms. Polar, like if you think about the word pole, like North Pole, for example, it means side. So polar covalent bonds means that they are sided. So the sharing of the electrons, that covalency, the sharing of the electrons together is sided, meaning that it's not equal. So non-polar covalent means that it's not sided sharing of electrons. So that would mean equal sharing of electrons. Equal sharing of electrons. Again, this means sided. So non-polar means it's not sided. So they are equal. Both sides are the same. Polar covalent bonding means that it's sided sharing, which means that it's unequal sharing of electrons. So what causes a covalent bond to be polar? That is electronegativity. And if you remember, we talked about electronegativity in chapter 6. Let's define it together again, just so we remember. It is the tendency for an atom to attract electrons to itself in a bond. So when we share electrons, we might share them equally or unequally. If it's equal, then it's nonpolar, not sided. If it is unequal, not equal, then it is sided. Sides are different. And again, what determines that is electronegativity. So if you look at the electronegativities on the periodic table, just to review, as you go down a group, electronegativity decreases. As you go across a period, electronegativity increases. The most electronegative element that we have on the periodic table is fluorine. Now, electronegativity doesn't really have units. It's just a number for comparison. So fluorine is the most electronegative atom on the periodic table. This corner, so francium, would be the least electronegative. And of course, noble gases, we don't really have any electronegativities for them. So let's say I make some pasta and I invite one of my girlfriends over for dinner. We both share the pasta. I, get a plate, she gets a plate. We have equal amounts. So that would be like we are forming a non-polar covalent bond. We have equal sharing. We're both getting the same amount. But let's say I'm having dinner with my husband. When I have pasta with my husband, he gets twice as much as I do. So even though we're sharing, it's unequal sharing. So that would be polar covalent. And so same thing happens with electrons when you are bonded. If your two atoms that are bonded together have similar electronegativities, they're both pulling those electrons, attracting those electrons the same amount, then you're going to have equal sharing. If you have one that it has really high electronegativity compared to the other, and the difference is great, then you're going to have unequal sharing. And that unequal sharing has different degrees. You can have somewhat unequal, unequal, really unequal, extremely unequal. And if it's extremely, extremely, extremely unequal, that would actually be kind of like giving and taking, and it would be like ionic. So this is just kind of a general guideline. If the electronegativity difference between the two atoms is really small, like between 0 and 0.4, like in HH, so, obviously if it's the same element, it has the same electronegativity, so there's no difference between them, and so they are going to equally share, and so that would be nonpolar covalent. So this would be equal sharing. I usually bring some candy like nerds to class, and I'll get two people and say, you take one, you take one, you take one, you take one, and we go back and forth, and so people are sharing equally. That would be nonpolar. Now, if you have something like HCl, H is 2.1, chlorine is right here, it's 3.0, and so the difference between them is 0.9. So it's bigger difference here. And so we'd say that's moderately polar covalent. So somewhat unequal sharing. Unequal sharing of electrons. All right, sharing here. So that would be like with my nerds example, if the first person gets 2 pieces, the next person gets only 1. And then we go to the first one, gets 2, 1, 2, 1. So they are sharing, but it's somewhat unequal. Next, what if your difference in electronegativity is even greater? So HF, for example, hydrogen is 2.1, fluorine is 4.0. That's a 1.9 difference in electronegativity. That's pretty big. So that would be very polar, very unequal sharing. Very unequal sharing. So let's say I go to the first person, tell him take 10 pieces of candy, the next person take 1, 10 and 1, 10 and 1. They're sharing technically, but it's very unequal sharing, and so that would be very polar covalent. Lastly, if the electronegativity difference is huge, like NaCl, for example, sodium is 0.9, chlorine is 3.0, so that's a difference of 2.1. That's huge difference. So that's as if I go to the first person and tell them, take 1,000,000 pieces of candy. The next person take just 1. 1,000,000, 1. Is that really sharing? They're not really sharing, right? The person who's getting 1,000,000 is getting all the candy. The other person's not really getting anything. So it's extreme unequal sharing that it's like giving and taking. And so that's what ionic bonding is. So it's actually a continuum. It's not, how we learned that ionic is metal with non-metal, covalent is 2 non-metals. That's not really 100% true. It's just that if you take a metal and a non-metal, the difference will be so great that it's going to be ionic. But in reality, it's really a continuum of one extreme is equal sharing versus the other extreme is very unequal sharing, extreme unequal sharing that it's giving and taking. So extreme unequal sharing, which really means gain and lose the electrons. One is taking the electron, the other one is not taking it at all. So again, it's just a continuum. You do not need to know these numbers. You do not need to know these numbers. All you need to know is the general trend that electronegativity increases across and decreases down. You also need to know that if there's no difference in electronegativity or very little difference, then it's going to be not sided, it's going to be nonpolar, equal sharing, whereas the more the electronegativity difference increases, then it becomes more unequal until it's extremely unequal, and that would be ionic. But you don't need to know the numbers. Now that's for just a single bond. What if you have a molecule that has more than one bond? So in order for the whole molecule to be polar, that means sided, which means the electrons are in one area of the molecule more than another. You would get a polar molecule, and in order for it to be a polar molecule, you'd have to have at least one polar bond, and that molecule has to be asymmetric. And we're going to talk more about this in a minute. But if your molecule is polar, again, what that means is that one end of the molecule has the electrons in it more than the other end of the molecule. Remember, electrons are negative. And so when you have a molecule, when you have unequal sharing of electrons, and let's say the electrons are here on this side of the molecule more than the other side, this will get a slight partial negative charge, and this will get a slight partial positive charge. That funny looking thing, it kind of looks like an S with a little extra part. That is the lowercase delta, the Greek letter delta, but the lowercase version of it, and it means partial. So that's a partial charge. So in a polar molecule, one end is slightly positive. That's the side that doesn't have as many electrons around, and one side is partially negative. So the whole molecule is not really sharing the electrons equally, is what that means. So that's sided. One side is partial negative, one side is partial positive. Because it has two different sides, we call it a dipole, or that it has a dipole moment. Di means two, pole means side. So it's a dipole, it means it's sided, it has two sides. To show that a molecule is polar, you can do a couple of things. You can show the partial positives and negatives. And so if you look at hydrogen and chlorine on the periodic table, you'll notice that chlorine is more electronegative. And so that means that those electrons that are being shared between the HCl are not spending the same amount of time with the hydrogen as they are with the chlorine. They're spending more time with the chlorine. And because electrons are negative, they get a slight negative charge, and the hydrogen gets a slight positive charge. So that's one way to show it, is by these slight positive and negative charges that we draw. Another way to show it is you draw an arrow towards the more electronegative atom. And so chlorine is the more electronegative atom, so you draw it like that. And on the other side, you put a little dash so it looks almost like a positive sign. And that's because this is partially positive, and then the electrons are going in this direction towards the chlorine. Okay, so that's what it means to be a polar molecule, meaning that one side of the molecule has more electrons spending time there more than another side. But how do you know that a molecule is polar or not? Well, it has to have two conditions. It has to have at least one polar bond, and it has to be asymmetric. Asymmetric means it's not symmetric. Because if it is symmetric, then everywhere is the same, and so it's not going to be sided, it's going to be nonpolar. But if it's asymmetric, not symmetric, then one side might be different than another side, and then it would be polar or sided. So how do you know? Well, you draw your Lewis dot structures first, and then you look at the symmetry. So I'm going to go ahead and draw these. I want you to stop the video and try to draw them on your own and see if you're able to draw them correctly. So come back when you are done. All right, hopefully you're back. And here are the different structures. I'm going to draw water in two different ways. Here's the other way that you could draw water. And let's look at these and determine whether they are polar or not. So, a couple of ways to determine polarity. One way is to draw these arrows that we talked about here in the direction of the more electronegative atom, and see if your arrows cancel out. That's really the correct way to do it. However, to do that, you need to be able to draw it with the correct geometry. So let's try that for CO2. And so carbon and oxygen, you look at each of the bonds, right? So carbon and oxygen is more electronegative. So in this bond right here, you draw the arrow that way. And in the other bond between the carbon and the other oxygen, again, oxygen is more electronegative, so you draw it that way. And you treat those as vectors. Hopefully you've studied vectors in math. Vectors are arrows that have direction and magnitude as well. But basically, see how this one cancels with that one? Imagine yourself in the center. So imagine yourself as the carbon, and one person is pulling you from this direction, the other person is pulling you from the other direction. And those two are equal in strength because they're both oxygens. Would you move? The answer is no. If they're both pulling opposite directions with the same strength, you would not be moving. That tells you that the molecule is symmetrical, even, and the electrons are being pulled in all directions of the molecule equally, and that this is nonpolar. Okay, the other method to do it, which I'd say works like 95% of the time, is to look around the center of your molecule. So right here is the center, and you look around to see if everything around you is the same. So right here you see a double bond O, nothing else. Everything around is the same. Double bond O, they're the same. If they're the same, that means that it's symmetric, it's all even, it is nonpolar. So both methods here are telling us it's not polar, not sided. Electrons are distributed all over in the same amount. Okay, let's look at water next. So water, hydrogen and oxygen. Oxygen is more electronegative, and so in here, that's one arrow. The other bond, that's the other arrow. So let's see if they cancel each other out. One is going this way, one is going that way. Do they cancel? No, they don't. They sum up to an arrow going this way, up, diagonally, right? So let me show you the sum of where they go. It would look like that, right? The oxygen here in this direction, that would be partially negative, and the hydrogens are partially positive. So that would be a polar molecule. They're not canceling each other out. Again, imagine yourself in the center of the molecule. Imagine that you're the oxygen. And you have two people in this direction, one here and one there, and you are pulling stronger than them. Would you be able to move them? Yes, you would, because if you're stronger, you're going to move them both this way. And so that movement, that tells you the direction of the electrons. The electrons are in this side of the molecule more than this side. So that's a sided molecule. That's a polar molecule. Now watch out. You have to be able to draw these with the correct geometry. Because remember, water looks like a bent molecule. And if you draw it as a bent molecule, you're going to get the correct polarity. But if you drew it this way, you know, you'd think that they would cancel each other out, right? Those look like they cancel each other out. So you're going to get the wrong answer if you do it this way. So you don't want to do it, you don't want to draw it that way. You want to draw it with the correct geometry. Remember I told you at the beginning of covalent bonding to draw your lone pairs adjacent to each other? That's why. Now the other method would have worked here to help you figure out that water is polar. The other method is you look at the center of the molecule and you check if everything around you is the same. So you look around you, see a single bond hydrogen, lone pair, single bond hydrogen, lone pair. Lone pairs are different from single bond hydrogens, right? If you have different things, that means it's not symmetric. They do not cancel each other out. So that would tell you that water is polar. Okay, let's look at CF4. So CF4, fluorine is more electronegative. So you got one this way, one this way, one this way, one this way. Again, remember that this is a tetrahedral, so you gotta think about it in the tetrahedral shape. And so they do cancel each other out. This one would be non-polar. The other method, let's check it. So you look at the center of your molecule, so carbon right here, and look around it to see if everything around you is the same. So single bond fluorine, single bond fluorine, single bond fluorine, single bond fluorine. Oh, looks everything is the same. That means it's not sided, symmetric. All the electrons are distributed in the same way, and so that would be nonpolar. Let's look at hydrogen. Well, this is definitely symmetric, right? There's not even a polar bond. They have the same electronegativity. There's no pull in any way, and so this definitely is nonpolar. You have to have at least one polar bond before you even check symmetry. But this is symmetric anyways. Let's look at the last one here. So this is ammonia. And so nitrogen is more electronegative than hydrogen, so you have an arrow this way, an arrow this way, arrow this way. Do they cancel each other out? They do not, right? The sum of all of them would be towards the nitrogen. The nitrogen will get a partial negative, and then these get a partial positive. So again, imagine yourself, if in doubt, imagine yourself in the center. So you're the nitrogen. And there are three people, and you're stronger than those three people, and you're pulling these three people, you're going to move up, right? So that's the direction of the electrons. You can always check with you know, whether everything around is the same. So nitrogen here is the center. Around it you see a lone pair, single bond H, single bond H, single bond H. A lone pair is different from a single bond H, and so that would be a polar molecule. So let's practice with the previous page where we took notes over Vesper theory, and let's try to figure out if these are polar or non-polar. So this one right here looks like it's all symmetric. You can look around your silicon, everything around it is the same, so that would be non-polar. I'm going to use NP for non-polar. Let's use a darker color. Okay, pH 3, let's look at this one. This one is polar. And for pH 3, it's not symmetric because around your central atom, there are different things. There's lone pairs and single bond hydrogens, those are different. If you were to draw the arrows, I think that phosphorus, they're very similar in electronegativity, but phosphorus is slightly more electronegative, and so the sum would be towards phosphorus. It'll get a partial negative charge, very slight partial negative, and the hydrogens would be slightly positive. SH2 right here, look around the center. There are different things, so it is polar. Lone pairs are different from hydrogens, so that is polar. Next one, BeI2 around the center. Same thing all around, single bond I, and so that would be non-polar. If you draw your arrows this way and this way, they cancel each other out. BCl3, you have everything around your central atom is the same. They're all single bond chlorines, and so that would be non-polar. If you draw your arrows, they all cancel each other out because they're all 120 apart. Now, just for fun, let's say I have 2 chlorines here, but then this is a hydrogen. Would that be polar? Yes, it would be. Or a fluorine here. Yes, it would be. Because the fluorine pulls in a different amount than the chlorine. So even if the angles are equal, the strength is different. So if you look around your the center of your molecule, and there are different things like single bond chlorine, single bond fluorine, those are different, it's going to be polar. Okay, next one, GeBr2. You see single bond bromine, lone pair, that is polar. It's not the same all around. Next one, AsF5. Center of your molecule, everything around it is the same, all single bond fluorines, and so that is non-polar. Next one, SF6. Again, center of your molecule, everything around it is the same, so that would be non-polar. And again, for all these that are non-polar, if I were to switch one of these fluorines with like a chlorine, then it would be polar. Okay, HCN, center of your molecule is right here. Looks like there's a single bond H, triple bond N. Those are not the same. That is definitely polar. It is sided. They're not all the same in all directions. Okay, last one here, C2H4. So the center of your molecule is right there. And you can see that everything around is the same. Top is the same as the bottom. Left is the same as the right. That is symmetric. And so that would be non-polar. Let's practice a few more. Let's look at worksheet 3. Let's look at this one. This would be polar. Let's look at this one. That is also polar. They're not symmetric. N2, that is definitely symmetric. That is non-polar. Water, not symmetric. Top is different from the bottom. In the center, lone pairs, single bond hydrogens, they're different, so this is polar. Next one, PF3, again, polar. Everything around the center is not the same. Top is different from the bottom. Same thing here. This one's also polar. You have lone pairs and single bond chlorine, so those are different. Definitely not symmetric. Let's look at H2. That is non-polar. It is symmetric. You don't even have a polar bond in there. Br2, same thing, non-polar. If you look at the center, everything around is the same. Same thing with this one, everything around it is the same. Same thing with the center of this one, everything around it is the same. Same thing with this one, and this one, and this one, and this one. All of these right here are non-polar, because if you look at the center of the molecule, everything around is the same. Top is the same as the bottom, left is the same as the right, and so these would all be non-polar.